Okay, let's look into calculating the enthalpy of a reaction using enthalpies of formation. So for the combustion reaction of acetylene that leads to formation of CO2 and water, we could be given the enthalpy values of each corresponding reactant or product, and those enthalpy values are understood to be formation values in regards to each individual molecule present in this equation. All the values are in kilojoules per mole, and I just want to highlight the fact that for elements in their elemental form, the value of delta H formation is 0. Because after all, the definition of delta H formation is formation of the species in question from the elements that make up that species, right? And since O2 is literally the element in its elemental form, that's already the benchmark, right? That's the 0 mark for the delta H values that we associate with formation. But what we do to determine the enthalpy of the reaction is to simply multiply the delta H of the products by their balancing coefficients, and then we add them all together. And we do the same thing for the reactants. We multiply the delta H of the reactants by the coefficients, the balancing coefficients of the reactants, and we add them up together. And then the whole term from the reactants gets subtracted from the products. At the end, however, you do need to divide this by a reference number of moles. In this case, I'm going to refer it to C2H2. But in the absence of that kind of information, you could technically use any of the molecules as reference. So that's something to be kept in mind. But to be most exact about it, you have CO2 as a product and 4 molecules of CO2. So you will multiply the delta H formation of CO2 by 4. You multiply the delta H formation of water by 2. You will multiply the delta H formation of C2H2 by 2 and the delta H formation of O2 by 5. And that sets up your products minus your reactants, all divided by the number of moles of C2H2 in this case, which is 2. So what you basically do is you just input the values of delta H formation, multiply them by the balancing coefficients, add them together, subtract the total value of reactants from products, and then divide it by the number of moles that you're referencing. So in this case, we have a value of delta H of reaction of negative 1299.5 kilojoules per mole of C2H2. And that's what you typically do for delta H's formation. Hopefully that was a bit of a refresher more than anything else. Now Hess's law is technically using equations for which you already have delta H's of reaction provided, and you use those equations to ultimately, upon applying changes to them, add them up together and yield an equation for which you yet don't have the delta H of reaction value. So for instance, we could look at acetylene reacting with water and H2 to yield ethanol and ask ourselves the question, what's the delta H for this reaction? And if you're provided with a set of equations like the ones that I'm showing here, then what you have to do is manipulate those equations so that when you add them together, you end up yielding the desired equation you're looking for. So we're going to apply that entire process and see how it works out. Alright, so first things first, let's take a look at the first equation. Specifically, let's pay attention to the fact that the product that we're trying to make is C2H6O, and the only equation in the series that contains C2H6O is the first one. We need that particular reagent to be on the product side, which is already where it's at, and we need only 1 mole of it. So what this is telling us is that the first equation already has the correct amount and of the molecule that we're looking for and in the correct place. So that tells us that the first equation cannot be changed. If you multiply by a number or you reverse or you do anything to it, you will change the proportion of C2H6O, which will mess you up when it comes down to getting the final equation. So right now we know that we have to keep the first equation intact. We're not going to touch it or move it. So then we move on to the next part. And we see here C2H2. The only equation that has C2H2 is the third one, which I'm highlighting now. We want C2H2 on the reactant side, and we do have it on the reactant side, but we only want 1 mole of it, whereas the third equation has 2 moles. So that tells us that we need to multiply that entire third equation by 1/2. That will reduce the value of C2H2 to only 1, the amount of O2 to 5/2, the amount of CO2 to 2, and the amount of water to 1. And of course, you also need to multiply the delta H value by the 1/2. So it does go down to negative 649.8. All right, so right now we have the correct amount of C2H6O in the proper place. We have the correct amount of C2H2 with the right amount in the proper place. So the first equation and the third equation are both locked in place. So now let's take a look at water. Okay, so or actually you could look at let's look at water. That's fine. So if we look at water, we need water on the left side of the equation, right? Now here you have to be a little bit careful because you do have water in multiple equations. Specifically, you also have water on the third equation. But the thing about the third equation is that we already locked it in place because we applied changes to it so that we'd end up with the exact amount of C2H2 we need to have. So the water that we have on the product side is automatically stuck there. We can't change that amount and we cannot move it to the left side because by doing so we would change the amount of C2H2. So the fact that we need to end up with water on the left side of the equation means that for the fourth equation that we haven't yet looked into, what we need to do is reverse that equation and put the water on the left side. And the one thing I want you to notice is that upon reversing an equation, what happens to the sign of delta H is that you change it. Initially it was negative 285.5. Reverse the equation, now it's positive 285.5. All right, second thing, we have we want only one equivalent of water at the end, and we do have the one equivalent of water on the product side in the third equation that cannot be changed. So that tells you that the water that you have on the fourth equation needs to be ultimately multiplied by coefficient to make it work out. And I'm going to apply that in a little bit, but just be aware that that can be done right now if you want to. All right, next thing. Take a look at the second equation. In particular, pay attention to C graphite. As you can see, nowhere in the desired equation do we want to have C graphite. So that tells us that we need to cancel out the C graphite completely from the equations. Currently, the first equation that is locked in place has two graphites on the left side of the equation. So that tells us that we want to place the graphite of the second equation on the right side. So we're going to go from having negative 393.5 to positive 393.5. And because we have two equivalents of C graphite on top, we're going to have to multiply this entire equation by 2, such that when you apply the 2 to all the equations, the C graphites cancel out. And in addition, when you multiply the whole equation by 2, you also multiply the value of delta H by 2. Alright, so that will cancel out the C graphites. Alright, now let's go back to this water business. As I stated before, you have one water on the right side, and right now you have one water on the left side, but you do need to end up with one water on the left side overall. So you're going to have to multiply the third equation by 2. Another way to look at it too is that you want to have only one equivalent of H2 on the left side, and currently you have 3 equivalents on the left side for the first equation, but you have one equivalent only on the right side of the fourth equation. That will only give you, or that will give you actually 2 H2s, which is more than what you need. So this tells you, either from the point of view of water or the point of view of H2, that equation needs to be multiplied by 2. So that will give you 2 waters, 2 H2s, O2, and of course you will double the amount for delta H. Alright, now what can be seen right now is that yes, the C graphite is going to cancel out. We know that was going to happen because we made it that way on purpose. But take a look at the CO2s. The CO2s also cancel out, 2 on the left side, 2 on the right side. Then your oxygens, this is actually kind of interesting. You have half oxygen on the third equation, 5 halves oxygen on the third equation. 1 half plus 5 halves is the same thing as saying 6 halves, which is equal to 3. And if you look on the right side, you have 2 O2s and 1 O2, which is also 3, so they fully cancel out. Alright, then the 3 H2s partially cancel out with the 2 H2s to leave you 1 H2 on the left side, as we want it to happen. And then the 2 waters partially cancel out with the 1 water on the product side to leave you only 1 water on the left side. And so if you add up all the equations the way they are right now, you end up with a desired equation, which tells you that you can now add up the values of delta H together. This particular procedure is to be contrasted with what we did with equilibrium constants, whereby adding equations had to be complemented with multiplication of equilibrium constants. But when it comes down to delta H and the upcoming thermodynamic parameters, if you add equations, you add the delta H or whatever thermodynamic values you have. All right, so that takes care of the delta H derivations, either from enthalpies of formation or Hess's law. So in the next video, we're going to talk about constant volume. So see you then.